Today I will talk about the model of vibration. And today we will working on the vibration high over X. And we always assume the space Y is a simple connected. And we assume the characteristic of the field is 0, and one of the cohomology group of X and Y is finite type. Okay. Our goal is to show the model of fiber or vibration is exactly the Sullivan fiber. So first, I give the definition of the Sullivan fiber. Consider relative solid algebra. And this is the argument from the CDG to the field. And we have Sullivan fiber. Through the push-out diagram. Okay.
I think it's should be the other angle.
This one? No.
Anyway, so let's look at this diagram. The diagram shows the push out in the category of CDJs.
Yeah.
Now, this push out is also the homotopy push out. Why? Maybe Alexei can explain it. So we have a diagram, and it's a push out diagram by definition. Very well. Why does it calculate the right push out in the homotopy category? In other words, why is the push out the homotopy push out?
I think there is a equivalence between opposite homotopy categories.
No, we can't. No. We can't use it because we actually used the Eilenberg-Moore theorem when we proved that the two categories are homotopy equivalent.
Okay.
And moreover, we don't need we don't need it here. The statement is purely categorical. So suppose we have a push-out diagram. Suppose that all three objects are cofibrant, and one of the arrows, but not the other one, is a cofibration. Then the diagram calculates the moment of the push-out, meaning the regular push-out is the moment of the push. It's a useful thing. It's a useful thing to know, and so if we somehow know that B is Sullivan, then the answer we get in the bottom right angle is the Hamilton push-out of the diagram. If B is not Sullivan, then we're out of luck.
Okay.
Maybe not, but we can't use the general nonsense in this case.
Okay.
В некоторых случаях push-out это гонометрический push-out, а pullback это гонометрический pullback. Это не всегда, но в некоторых случаях. В частности, если у нас три объекта как кофибрант, надо из них сделать кофибрацию, то тогда все окей. Значит, иначе может быть не окей.
Okay, we will explain why this is called Sullivan fiber. So let's consider this is a fibration. This is a fibration, and this is a base point with fiber F. We apply the APL factor, so we'll get maybe I'll give some also write by this is okay. And there is a Sullivan model. The PRX. So we have the diagram. Identity. And there is a unique, there is a map bar. So this is because we use the push-out property, and we want to prove this is a quasi-isomorphism.
There is a map by general nonsense, but we want to prove that this map is quasi-isomorphism, which is non-trivial.
Yeah.
It doesn't follow from general nonsense.
Okay, so today our goal is to prove
as we saw, APL considered as a function from top to CDJ
Yeah.
is actually neither a left inverse nor a right inverse. Neither a left adjoint nor a right adjoint. So it doesn't really have to preserve limits or co-limits. But if we pass to simplicial sets, then APL becomes a left adjoint, so it preserves co-limits, which means it takes co-limits in spaces to limits in algebras. Very well. But here we have a limit in spaces of this diagram, and a left adjoint doesn't need to preserve it. But still, it turns out it does.
Okay. Do we need to explain this map? I mean, if anyone don't know, I will explain.
Let's have a look at the diagram.
Okay.
So, does the map denoted M make any sense? Jipping claims it's just a push-out property.
Yeah.
Do we agree or do we not?
I agree.
Alexei? But just M.
Yeah, just this map. If you don't know, I can explain more detail.
I think it's cheated.
Oh, okay. Our goal is to show M bar is quasar isomorphism. So I will first explain the M is what. We consider generally. Consider Sullivan model from to I mean this is a Sullivan model of morphism. It's quasi-isomorphic to such that relative Sullivan algebra, and we have the follow diagram. Okay. So, do we need to explain what is the relative Sullivan algebra?
It's basically the same as an acyclic vibration.
Yeah.
And we already know that every map, in particular phi, can be written as the composition of an acyclic vibration followed by vibration. Well, we just take the first error in the composition and we get the relative Sullivan algebra.
Okay. So So how to prove this is a quasi isomorphism, we just use the Edinburgh-Moore theory. First, we state this. I just write this theorem. That D is we denoted is a commutative diagram of complex and we can choose a symmetry resolution. Okay, I will explain what is the symmetry resolution after write this. Modulo. It's a quasi isomorphism. We can get another diagram. We denote it by B prime. And if D is weakly equivalent, I will explain this. What is this mean about weakly equivalent to the another diagram. C star is the singular coaching functor. Sorry. Then we get MB hat is, oh, okay, MB hat is here. With the isomorphism. Okay.
So let's see. We have several diagrams.
Yeah.
We have the diagram with APLs, which is the one here. It contains the map M bar, and we want M bar to be a quasi isomorphism.
Yeah. I will explain how to get the.
Then we recall what the classical Eilenberg-Moore theorem is about. It's about the diagram on the second board from the left. So Eilenberg-Moore prove that if we take coefficients in basically in an arbitrary ring, maybe a principal ideal domain, I don't remember, maybe not. co-limit, not the co-limit, the homotypic co-limit of the diagram on the at the bottom of the second board is quasi-isomorphic to C alpha star of F. And basically, the Eilenberg-Moore theorem is more general. We can replace the bottom map by an arbitrary map of C alpha star of Y to C alpha star of Y prime, where Y prime is another space, an arbitrary one. Then the homotype limit co-limit will be a model for the singular chains on of the induced vibration. So two parts in the argument. One is the Eilenberg-Moore theorem, and the other one is juggling the diagram so as to see that this one is quasi-isomorphic to that one. Chipping, does what I say make any sense?
Yeah.
Okay, so these two parts are separate. The second one is easier. So let's maybe firstly prove that this diagram without the this diagram, meaning this diagram, is quasi-isomorphic to this diagram.
I will explain this.
Yes, and then if we have two diagrams which are quasi-isomorphic, we don't need to say anything about semi-free modules and the rest of it. If we have two diagrams which are quasi-isomorphic, they must have the same homotypic co-limit. And we know that the homotypic co-limit of the diagram on this board is the Sullivan fiber as we defined it, and the homotypic co-limit of the other diagram is the co-chains on the fiber, on the cell fiber. Hold on, please.
Okay.
So, okay. So we first identify two diagrams of unfortunately not necessarily commutative DJs. The singular co-chains are not commutative, even rationally.
Yeah.
And then we prove the Eilenberg-Moore theorem about the homotypic co-limit of the diagram on the second board.
Okay.
Так, имеет смысл только сейчас сказать, или она не имеет никакого смысла? Значит, у нас есть две диаграммы. Одна считает сульвановский слой, другая считает слой в смысле расслоения. Ну, давайте сначала отождествим вот эти две диаграммы, то есть докажем, что они квазизоморфны друг другу в сборе таких диаграмм. Тогда геометрические пределы, точнее полпределы будут квазизоморфны, и останется заметить, что в первом случае у нас геометрические полпределы будут просто по определению вот это вот лямбда v с d чертой, а в втором случае геометрический полпредел, вот эта вот нетривиальная часть, он равен, точнее квазизоморфен коцепиан на слое в смысле расслоения. Вот, но давайте сначала отождествим диаграмму.
Okay. So if we know this theorem, we just use this theorem can explain why this is quite a isomorphism. You just take the diagram D is this one, and maybe can write it. And you consider this is D, and D prime is the Solian model.
Let's pay attention to what's happening on the board.
And you consider the other diagram is also same thing. Maybe it's all this, and we know D and this one is quasi-isomorphic. So for any x, so we know in this case MB hat is this M hat, so you will get this is a quasi-isomorphism. So
does anyone or everyone agree with what Jipping has just said?
thing.
Имеет ли смысл происходящее? Does what is currently happening make any sense?
Yeah, maybe this is just a query. So
If it doesn't make sense, then please ask the speaker.
okay. So we need to prove this theorem.
Which theorem? Which theorem?
Yeah.
By choosing module, we do what exactly?
With quasi-isomorphism.
Yes.
Yeah.
So the statement says by choosing, and then what?
And then we consider this diagram. You just tensor the field. Yeah. This is one part of the statement, not of the full part.
Okay. So this part is more or less clear. Let's this statement is more or less clear, but okay. So
So
suppose that we have a model for
Y.
y. And but we suppose we take a model for x, which is obtained by taking an acyclic and we're taking I want to replace this error by a configuration. Suppose I'm able to do that. This is in fact possible by general nonsense. And k remains the same. So suppose we have where we were able to construct a commutative diagram like this. Now. Well, we can't really do anything with this with this diagram. We want to apply the Allen-Moore theorem. So we want to take this diagram and somehow attach it here. How does this work? So the idea is if I can replace if I take the homotopy co-limit of this diagram, I just get the Sullivan fiber as we've just defined it. Now, on the other hand, if I take the homotopy co-limit of this diagram, no, of this one, we get C of a star of F by the Allen-Moore theorem, by the classical Allen-Moore theorem. How are the two diagrams related to one another? Well, are there any suggestions? Значит, еще раз, у нас есть, есть нечто, есть другое нечто. Мы знаем, что копредел, гомотопический копредел одного нечто это сулеймановский слой, а гомотопический копредел другого нечто это слой. Вот мы хотим понять, как одно нечто связано с другим нечто. Ну, для этого нам нужно вспомнить теорему Дирана. So, my claim is one can probably no one remembers, but we did prove at some point that the APL
the quasi-isomorphism to a single thing.
APL is quasi-isomorphic to singular cochains,
Yeah.
but not directly.
They have another object.
Yes, so let's try to remember what the intermediate step in the proof was. Значит, вот эта штука, она в буквальном смысле не изоморфна сингулярным коцепиам, тем более как пункт. Значит, на этот счет мы долго мучились с теоремой Дирана. Чтобы все-таки сказать, что они, значит, что вот это, значит, что функтор АПЛ, он квазизоморфен функтору С звездой с коэффициентами в куб. Долгие были мучения, там, значит, там 2 занятия, там, значит, прямого изоморфизма нет, квазизоморфизм. А какой есть? So, there's direct way to identify APL and C upper star, but there is an indirect way. What was it? Meaning there's no direct arrow going either way, but there is a roof of arrows. Okay, no one remembers. That includes me. So we're wrong. Комплексно черха, который значит, как отождествить апрель и значит, сингулярный кассет? Sorry, it wasn't just one roof. There was there were several arrows in the sequence. I think there were four arrows. Well, so the arrows go as follows: APL of X. So
There's total of what's PQ and check, yes.
so briefly, we take the total. We take the check complex, which corresponds to the covering of our space, where our space means the geometric realization of the singular co-chain complex. So it's very large. But anyway, so this is the -1 column embedding, and this is the -1 row embedding. And if we so if we do this with APL, we can compare the APL of X with the
Well, in my notes, I found it says we can do the same with C star.
yes. So basically, we take two functors, C star and APL separately, and I think this is not -1 throw. This is the 0 throw, and then we show that both of those give rise to double complexes. The double complexes are different, but both are quasi-isomorphic to the 0th row. So we pass from APL of X to the total complex of the double complex, then to the 0th row, and then we identify it with the zero throw for single go chains and do the same. So there's a sequence of quasi-isomorphisms, but they're all functorial, which allows us to identify this diagram, my k C alpha star y, C alpha star x with this diagram. Now we want to now we have identified what the two diagrams and the homotopy co-limit of this one is the Sullivan fiber. This much we know. But are we able to prove today that the homotopy co-limit of this one is the C alpha star of f?
Yeah.
Are we ready to prove that the homotopy co-limit of this diagram is this one?
No, I use the theme-free model, so.
Okay. So the Eilenberg-Moore theorem, which is a non-trivial theorem, says that if we take this thing, then the homotopy co-limit of this thing is quasi-isomorphic to C upper star of f. This whole story about choosing a semi-free blah 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 and the rest of it, in fact, serves to make sure that we calculate the homotopy co-limit and not just the co-limit of some diagram. Look at this diagram. None of the algebras is covariant. None of the maps is a covariation. So clearly some modifications are necessary to calculate the homotopy co-limit. Let's rephrase the question. GP, are you ready to prove that after some manipulations with these three ingredients, we get something quasi-isomorphic to this one?
Yeah.
Okay,
Yeah, I have this
so
part.
let's prove this because the rest we sort of understand already.
Okay.
Okay.
Yeah.
Well, at least that's my impression. I might be wrong. Значит, у нас есть несколько вот таких вот штук, у которых я делаю пушарты. Значит, один из них мне дает слой Сулливана по определению. Значит, а вот есть еще другой, и значит, что с ним делать неизвестно. Он вообще не коммутативный. Значит, я хочу дальше понять, что такое пушаут, значит, монотипический пушаут вот это. Здесь вообще we're in trouble. Another source of trouble is that this diagram lives in non-commutative algebras, associative but not commutative. Well, this one Now I don't understand anything. Great. Значит, есть коммутативная алгебра, есть некоммутативная алгебра. Это разные категории. Значит, функтор вложения из коммутативных в некоммутативное в какое сопряженное? Право или лево? Непонятно, но мне кажется, что все-таки право. Значит, тогда этот функтор он совершенно не обязан сохранять полпредела. Топический никаких. Значит, и, соответственно, топический полпредел этой диаграммы, он вообще не имеет никакого отношения к топическому полпределу этой диаграммы. Вот, и что делать? So what would you, as Sasha said, the two diagrams live in different categories, and there's a function between those two categories. But this one is a right adjoint. It's not a left adjoint, it's a right adjoint, so it doesn't preserve, doesn't need to preserve k-limits. Okay, let's prove that some procedure applied to C alpha star of x, C alpha star of y gives us the C alpha star of f, and then we'll see if it helps or not.
So why we need this symmetry module? Because if we have a Solian algebra, it is a symmetry module. This is maybe a lemma. I mean, when you have this theorem, you want to get this is a quasi-isomorphism. What is your MB? MB is exactly the Solian algebra, relative Solian algebra, and maybe there is some lemma if a relative Solian algebra is exactly a symmetry module. So I will give some explain about what is a symmetry module. It's called symmetry R. If M is M have a filtration, M is a union of filtration, and such that M0, M1 quotient, M1 quotient, and -1 are free. Okay, let's prove the theorem. We use another theorem to prove the Edinburgh-Moore theorem. Pi is a fibration, and this is a fiber of the base point at the base point y0. and we have the semi-free module. We consider it as a C star Y module. Since we have the map from C star Y to C star X, so we can consider it a C star Y module. Then and we have the diagram. This is isomorphic to tensor model, and this is if my is quasar isomorphism, then we prove my at quasar isomorphism. So first we prove this theorem, and then we prove the Allenberg-Moore theorem. Use this theorem.
Why? Well, firstly, there's an error message. And secondly, why is this true?
Why this is true?
Yes.
This is implied.
Yes.
Yeah, I want prove this and then use it to prove Allenberg-Moore theory.
Okay. Well, let's have a look at this. Okay, what is W? In this diagram, there is a W. What is W?
Yeah, W is a symmetry resolution in here. You just choose a symmetry resolution.
W is the symmetry resolution.
Yeah.
Symmetry resolution of what as what? So there's a W, and there is MY.
My is a quasi-isomorphism. You choose a symmetry resolution. Yeah. So maybe no, not if.
Okay, so X goes to Y.
Yeah.
And we resolve C of X
As a
as
Y model.
as a C of Y module. Very well. So what we have, so W is just a model.
Yeah, yeah, yeah.
It's,
Yeah,
it's
maybe.
not an algebra.
Yeah, it's just the module.
Okay, so here we have M and here we have W. Is it the same?
Yeah, yeah, yeah.
Is it not the same?
No, this is not M, this is W. W. I write the type.
Okay, so
Okay, so sorry.
problem. Okay, so we resolve the. Okay, where does NY bar come from?
You just take the tensor product.
Okay, we take the arrow on the right and tensor product with K C star,
Yeah.
and we get over C star Y, and on the one hand we get W. I agree, but why do we get C star of F upstairs? We take so the vertical arrow is in fact a quasi-isomorphism. This is how we construct it.
Yeah, yeah.
Very well. The question is why do we get C upper if we take C upper star of X and tensor it with K over C upper star of Y. Why do we get C upper star of F?
Okay, why this? Okay, I will explain this is why. Exactly the C star F. Okay, we can consider a general case. We consider a general case. And we have a pullback vibration. Follow the diagram. And since we have a symmetry module for C star F, so we can tensor C star Y, C star Z, as a symmetry module for star X Z. And what is the construction of this map?
Yeah, the construction of the map is clear.
Okay.
What is not clear is whether or not this map is a quasi-isomorphism.
This is a quasi-isomorphism?
Yes.
This is what I want to prove. Yeah. We know this is a quasi-isomorphism. We want to prove this is a quasi-isomorphism.
Once again, I do not understand how we get C upper star of f, or a map into C upper star of f.
You mean you wonder why this is mapped to C star f?
Yes.
Yeah.
Yes. We. Basically, the my bar is obtained from my by tensoring. Tensoring over k.
Yeah.
Tensoring by k over C upper star of y. So what we need to understand is we need to understand why why do we get C upper star of f if we take C upper star of x and tensor it by k over C upper star of y. So this is what is not clear to me, it's not clear whether or not there is a map in either direction. So is there a map from one side to the other, or the other way around?
C star f.
So this is necessary in order for me to understand this diagram. I understand this arrow.
Yeah.
I do not understand this arrow.
Yeah. I want to see if we consider a general case, if we have the the special case of y0, you construct the MZ the exactly the my head.
Okay, well, let's have a look.
So I will construct.
Let's look at this. In this formula, what is my? My is probably.
We have know what is my. We don't know this map. We construct this map.
Well, before we construct the map, I understand the right-hand side. I understand C upper star of Z, but I do not understand my in this formula. What is my?
My is the same thing. Yeah, you have
okay.
a similar.
So my is well. Let's write it here. My is C upper star of y times a double.
Yeah.
Well, please write it on the blackboard. Okay, but then the map what we get by tensoring the small my by k is not the same.
Yeah. We want to construct this map like.
I do not understand the map MY bar in this diagram. Can you please explain it?
Yeah. I want to see if you have this map and you just consider the base point, you will get this is just my bar.
Let's look at the source. The source is k times my.
Well, I write down the construction of this map.
Now, yes. This map makes sense very well, but where do we get this map from?
This map?
Yes.
This is just the fabrication in the diagram.
I don't understand. So you claim that there is this map. Why? How do we construct this map? General nonsense. Actually we can't use the general nonsense because my, the capital My is just a module. It's not an algebra.
Yeah, this is a little my. This is a map from my to C star x, and then you take to the C star x z.
Okay. Does anyone understand why what this map MZ is? So Jiping, could you please explain what MZ is? So we have C upper star of Z. Tensor over C upper star of Y, C upper star of Y, which means C upper star of Y cancels. Tensor W.
Yeah.
So essentially we have C upper star of Z, tensor W.
Yeah.
And tensor over K. Very well.
Yeah.
What is W?
Okay, maybe you just consider V is the element in capital My. I don't. So you have a little My. Now go to C star x, and then you go to C star xz. Since in special case you consider the point and the exactly the k, although this tensor is exactly W, so you get M Z in the special case is my hat.
Let's try to figure it out. So here we have C upper star Z cross W.
Yeah.
And we want to map it into C upper star
Yeah.
of X times Z. So how do we do this? Right, let's remember what W is. W is
Vector space.
well, W isn't really anything. It's just the set of generators, the space of generators for the free resolution. So free resolution of semi-free resolution of C star X as a C star Y module. Very well. So we have okay. Does anyone understand what's going on?
More or less.
More or less. Okay. So the thing is, we have a map. We have this map. This is something we have by the construction of W.
Yeah.
And what we want is this map. So how do we get this map from this one? We have this arrow, again the clear diagram, and this arrow. So we have the bottom arrow, and we want the top arrow. So what do we do? And what do you think? Yes.
So we have arrows to the
Yes. Did I mess up the arrows? So it goes. Yes, I did mess up the arrows. So we actually have Z, which goes to Y, which means C upper star of Y goes to C upper star of X. And similarly, X, Z, the pullback goes to X. Very well. So the map is maps should go from X to XZ. But still, we have the bottom error and we want the top error.
So the logic is that xg is complex, so this is a push forward. So Cicero is a push forward. This must be the logic.
This would be valid if C on the star were some kind of a left adjoint. And it is in fact some kind of a left adjoint if we consider it on the so if we consider C of the star as a function from simplicial sets to DJs, then it's indeed a left adjoint. So the left adjoint preserves colimits, but not necessarily limits. Here we have a limit. XZ is the limit of the diagram, which is so I suggest we have a break.
Okay.
During the break, let's think about this diagram, and then we'll continue.
Okay.
Okay. 111.
Few times.
Okay, okay, thank you. So,
we have this question mark. Are we any closer to understanding why we have this mysterious map? Can anyone help chipping?
since we have this diagram, and yeah, this one we have, and we want these two tensor MY. Yeah, yeah, we want to get if here we tensor MY, here we also tensor MY, and here we this is little MY.
Well, W is not really a module for anything.
Yeah, yeah.
It's more like the space of generators for the free resolution.
Yeah, yeah.
On the other hand, if we have this map psi, it induces a map of rings, and it also induces a map of modules. More precisely, it induces two functors between the categories of modules.
Yeah, yeah, maybe this is the
That's the
tensor identity. Yeah.
again, there's the right adjoint and the left adjoint, and the trivial one is the right adjoint, and we is this one the one we need. So basically, we have the restriction of scalars and the extension of scalars. There are two extensions. There is the tensor product extension and there is the Helm extension. Well, let's use the tensor product extension. Then, yes, the restriction of scalars is both the right adjoint, is both the left adjoint and the right adjoint. So, okay, so if we consider it as a left adjoint, then does it help? No, it doesn't really help because it takes the module of y as the same module over x. This is not really what we're after. Okay, so let's look at what it says on the board. Okay, what is my my's resolution for CX? Then we why do we just tensor product? So we take the tensor product of the bottom line with the resolution for CX.
Yeah.
And why? How do we construct the vertical arrows then? This is something I don't understand. We have a resolution for CX, very well, but then how do we get the diagram on the right, in particular the vertical arrows?
I remember you can take, you don't consider this is a CW, CCY tensor W, just consider it together. You take an element like this. And
well, C tensor Y tensor W is...
yeah, you also can
just,
consider C tensor Y the tensor W.
Well, the notation C tensor C of Y tensor W is a bit deceptive. We don't take the tensor product of CY with some module W.
Yeah.
W is not really a module. It's more like a space of three channels.
Okay.
Now basically we need to make sense of C star X, C star Z tensor W. What is it? One could say that we take the same generators as below, and we define the differential on them using the fullback from Y to W. I have a generator, some element of a basis of W. Okay, I know what the generator, what its differential is in C of Y. Very well, I take the fullback into C of Z and get something. Which probably works as a differential. let's assume that we have this this map marked question mark and continue.
Okay. Okay, now we need to prove my hat is quasar isomorphism. So that's step one. We can choose a CW complex. We choose Z is a CW complex and fix the base point. And you can compute this map if we know this map. You can compute in this map, and firstly you have the CW complex, and this is a weak hold. So firstly, you have the cohomology same thing. So it is also satisfied the hypothesis of the theorem. I mean, they is finite type, and you consider if we know this map. You can to compute this thing their theme. Maybe we should compute why they are same thing. Maybe we can see this is true, since I think time is very limited. So if we have time, we will see why this is true, and then we assume Y is CW complex.
Let's assume that everything is a CW complex.
Yeah. Actually, you just need Y is the concept, I think. Okay, so next step, we want to construct another sim-free module. We want another sim-free module. H where H is the cohomology of the fiber. Okay. This is the most important step in the proof. So, and we prove this by induction. So H is a cohomology, and theta is a cohomology with 0 different to the C star F. And it satisfies his identity. You apply the cohomology functor. So okay. So let how to construct the suppose okay, and we need to explain more. And such that for this and mu y okay. Actually, this condition can imply why this is a sim-free module.
So what is M?
M.
There's an N in what we've just written. D from Hn to.
Yeah. H is cohomology.
Yes, H is the cohomology.
Yeah.
What is N? N.
For all n. Actually, we need this property to satisfy his sim-free module.
H is the cohomology of the
Yeah.
fiber
Yeah.
such that.
Yeah.
But then D goes from Hn to blah blah blah.
Yeah.
Does anyone understand what's happening?
Maybe we
What does this all mean? D and Y bar, and so on. So could you please explain the gradients? So we have some D from Hn to blah blah blah.
yeah.
Okay, what is this D? What is it?
There is a differential in here. We need to construct it. So, and he satisfies this. If he satisfies this property, he will be a sim-free module. And why he satisfies this? We need to prove, and we use theta is quasi-isomorphic, and we will
Does anyone
maybe.
understand what's going on?
So y hat is this thing and the same thing in this diagram, and we need to prove this is exactly theta.
Yes, we need to prove this.
Yeah.
Okay.
So what's the relation between mu y and
Mu y is we need to construct mu y, and is a semi-free module, and
Yes, we don't have it. We want to construct
Yeah.
This whole collection of data. We don't have it yet.
Yeah.
This is what we want.
Okay. Suppose we do this by induction. So we have construction D and mu y. C star y is h less than, strict less than, and I need to extension the d and the mu y to n case. Let me see. Okay. Firstly, we have the exact sequence. The relative cohomolent singular chain. And this is and the second line. Zero. And okay, maybe this is the mu y. This is the mu y bar, and here is the alpha. Here we can by tensor identity. Okay. We have the exact sequence. Both two are also both exact sequence. And the next step. Oh, I want to explain why this map exists. Yeah. I want to explain why this map exists. Yeah, maybe this is because we compose these two map and he factors through R uniquely.
Sorry, I didn't.
Yeah, how to see?
Does anyone understand what's happening? Where does this all come from? Okay, so y is y naught is the base point.
Yeah.
So we have a map C of y naught to C of x mod f. So the C on top is relative C mod
Yeah.
fiber. Very well. Now we want to extend it. Once again, which are the arrows that we already have, and which are the ones we want to construct?
Why? Why this map exists? Maybe we can consider a general case. If we consider a general case. We have inclusion subspace, and we have this is the pullback. Maybe they are same thing for X. And you have symmetry module resolution. And the symmetry module resolution for XA. And you have exact sequence.
What does it mean? MA, C apostrophe A, over C apostrophe Y, and Y. So what is capital MY in this case? Shouldn't it be W?
Maybe we can write this as my. Okay.
Okay, good.
Sometimes I write my, sometimes I, because I want to see more space. And we have another exact sequence. The tensor. This is same thing. Okay. The special case is here, and you consider.
Does anyone understand what
This line is just
currently do?
Just a tensor. This line is just a tensor my, since my is free, so this is also exact sequence.
Wait a minute. So my is a semi-free CY module.
Yeah.
Which means, well, it's free as a CY module, but
Yeah.
it's not free as a DG module. Very well. So we take the sequence of the couple A comma Y, then Y comma A, and we transfer it by my over C apostrophe Y. So there should be a C apostrophe Y on the left as well.
Yeah. This is C star Y.
Okay, so let's assume the bottom y is exact. Okay, so we have the top line which maps and so the if we erase the ny's, we get a commutative diagram. How do we define the maps with ny's with the factors of my present?
You mean this map?
Yes.
Yeah, this is just a diagram changing. Since there is a unique map, the effect through this map.
No, I don't follow. Does anyone understand how to define how we define the vertical maps? Yes.
I think this is just a diagram changing.
What does it mean exactly that we're diagram change? Понимаете, кто-нибудь, как в этой диаграмме определены вертикальные строчки, в смысле вертикальные...
So this map is just inclusion, and this is inclusion tensor identity.
The horizontal ones are all right.
Yeah.
It's the vertical ones I don't understand. Если есть какие-то вертикальные отображения, значит, если мы не умножаем на my, тогда все понятно, а вот если мы умножаем, тогда мало что понятно.
Сейчас это же та же проблема, что у нас была.
Ну да, so this problem is similar to the one we've just discussed. So if we don't multiply by my, we have this map. On the other hand, if we do multiply by y, then what exactly is the map? And why does the diagram commute?
This diagram commute, and you just by.
We don't have this this diagram yet, so it doesn't make sense to ask whether or not it commutes. What are the vertical maps? In this diagram, it's not clear, well, at least to me, what the vertical maps are.
These two maps we have given in here, and
hold on. So my goes from
yeah.
So my goes from small my goes from capital my to c upper star of x. Very well. So
Yeah,
but this is just for my individually. So we have c star of y goes to c star of x, and my goes to c star of x. How do we get a map from the tensor product of the two of the c star of y? Well, here, well, basically here one could argue that after we tensor the c star of y, we just get a y, and so we have this map. Very well. So the one in the middle I understand. What about the one on the right?
This map.
Yes. So how do we get this map? So it says you just you just write it before the diagram. C upper star of A.
Yeah.
Tensor C upper star of y and y to C upper star of x. How do we get that?
I think this is a similar question for this question.
Yes. And well, there's a similar question on the left as well. We have an arrow, but how to construct it so that everything commutes.
I think the only way is the last page I write here. I remember maybe is the definition of the MA.
Yes, but it's not. It's not clear that such an MA does exist. We can always try to define it this way, but we need to show that the definition makes sense.
Okay. MA, you have an element in here. I have another element in here. You need to
Can anyone help Jimmy?
I think this is the last page I read here. You have my you can to C star X, yeah, and you can go to C star XA just by the inversion of the inclusion. Yeah, and then you multiply it by A. Right. And then we need to check this commute.
Well, what do we have? So we have. Okay, we have a map of. We have C of A goes to C of X and Y goes to C of X. So we have a map of and this thing commutes with C of Y. So we have a map of the tensor products. But then you want to multiply.
Yeah.
XA. This is the tensor product map. Does it descend when we take everything over C of y?
Why?
Well, probably yes, because
Yeah.
basically the only difference is the result is defined basically if we multiply something by C of y on the left and the right factor is the same as multiplying it on the right and the left factor. Okay, so the arrow marked in A is more or less clear. We just take the tensor products of the two arrows from C of A to C of XA, from my to C of XA, and then we take the product in C of XA. Then we descend it to the tensor product of y. Very well. What about the arrow on the left?
Okay. Yeah, this is so maybe this definition also true for the above discussion. I mean, there are same thing. I just read here or here last page.
Okay.
Yeah.
So the arrow on the left is similar, except we instead of taking the product of the product in XA at the end, we take
Yeah.
the product C of x comma XA tensor C of x goes to C of x comma XA.
Okay. You have this commute diagram, and then you will have a morphism.
Hold on. That's one more thing. If we okay, so here we assume that x to y is a fibration.
X to y fibration. Yeah. We also assume this is a fibration.
A is a subset of y. So A is not an arbitrary map, it's just a subset.
Yeah. This is my. Yeah. I also assume.
Okay.
Okay. So we have a map, and then the special case is here. You just take A is y0. So I need a notation. I write here as MYA, and I write here is y0. So there is a lemma, but I don't give the proof today. Where is my lemma? There is a lemma. My hat is key regular. I will explain why it is key regular. It can imply MYA is K plus 2 regular. Maybe someone know what is regular.
What is M bar?
M bar is I have sure maybe
Is the same as the M without the bar, or is it?
no and I have we can recall my is this is the resolution, scene-free resolution, and this is my bar. Okay.
And what does it mean for my bar to be K regular?
Yeah. I will explain what is called K regular. We see a morphism chain complex or morphism. Morphism is called K regular if Hi gamma is isomorphism is an isomorphism for I strictly less than k or strictly unequal, and Hi gamma is injective in the case of I equal to k plus 1. Okay, so we assume we have found in the strict less n case, and we know this mu y bar equal to sigma is n plus 1 regular. This is just by definition. Yeah. And so you will get mu y little y0 is n plus 1 regular. You just use the lemma. Now you can choose a basis of the nth cohomology, and lift the cocycle set gamma k to element maybe chi k in Cnx. Yeah. And we know d chi k is element in Cn plus 1 xf. So you can write dxk as a sum. First part is uk plus vk for uk is the element of cy0 tensor h less than, and wiki is element of xf. Okay. So you just know you can extension the definition of d and mu y. This is you just by d gam k equal to uk and mu y gamma k equal to chi k minus vk. Okay. So we construct the map. So we now have mu k and d. Okay. And now since mu, I just since mu we have no mu y bar equal to theta. We just recall something, and this is the isomorphism, quasi isomorphism. You just by quasi isomorphism. So we know which one is quasi isomorphism. Here is quasi isomorphism, and you can use the lemma again. You will get this is also quasi isomorphism. You just apply the lemma, and then you use five lemma of the short exact sequence. You can know this is the isomorphism. So now you have this diagram. This is a little my. This is mu y. And since this is a symmetry mode, symmetry resolution, you can extension the map.
Okay, so let's have a look. Once again, how do we get the top diagram on this board? So that the diagram involving C of x comma f, alpha, and so on. How do we get the vertical arrows in this diagram? So, for example, my.
No, this is not m. This is mu.
Okay, so why are we able to choose H as
H is home top.
yes,
Yeah.
this much is clear. But
Yeah.
why we're able to choose it as a set of generators for a free or semi-free resolution of x? So once again, where did we get the top diagram in this picture?
Okay.
Where do we get the diagram at the top of the board from?
Okay.
We are able to deduce it from the diagram at the bottom of the same board if we are able to choose H of F as as a model for as a set of generators of a model for x for C of x over C of y. Then we just here's what it says below, and why are we able to do this? Maybe you've already explained it, but I forgot.
Mm.
Следите, затем, что происходит. Значит, ну, на самом деле ничего сложного не происходит, но нужно просто значит, понять, вспомнить, что это означает. So we want to we want to deduce the diagram on top of the board.
Yeah.
And we want to deduce it from the one at the bottom of the same board because we sort of understand where the bottom one comes from. To do this, we need to construct a model for C star of x, which would be set at 3 over C star of y, and we want to choose the cohomology of f as a set of generators. Well, basically, how do we do this? If we want to have just one module structure, then what we do, basically could proceed by induction of some type or another. Which is basically sort of what's happening here, except I think we're a bit lost as to what exactly we induct on.
Maybe there's something wrong, I think. Okay, I think this here something wrong. Maybe here.
The second
I will check it again.
We somehow conclude that there's this the y, which is a quasi-isomorphism.
Yeah. I will check it again after the talking, and we get. This is also a quasi-isomorphism. So. So now we have a map from my to c star y tensor H, and what we want. And we can also use the property of the symmetry module. So this is a symmetry module. There are exact another map, another from my to c star x, such that mu y will minus my equal to dh plus hd. And this is a homotopy. This to map homotopy. Maybe this is this is.
What is M? Mu y O?
This.
Okay.
Maybe we choose another type, another notation. Okay. But I should be careful for this.
Well, yes. Well, I think we've got it.
I should be careful for
Okay.
the existence of this mu y come. Yeah.
Yes. And what is mu y? Sorry. What is my? My is.
The
I thought my is precisely what it says on in the top right corner.
yeah, my is also the original symmetry resolution. Yeah, why this exists since they are symmetry.
Okay, I'm lost, but never mind. Is there anyone who is not lost? No, there's no one. Okay, so let's summarize what we've done.
Okay. My is also the symmetry.
It's sort of plausible that there is such a model, C star of y tensor H. Okay.
Yeah. This.
Now, okay, so let's summarize what we have shown.
Okay. So you use this property, you can get H gamma. H 然后 and this is a isomorphism in homotopy category, and this also so you get this is a quasi isomorphism. Yeah. No. The quasi isomorphism, and then we tensor K. It's also a quasi isomorphism because you also need the property of the resolution, symmetry resolution. Here we also use some property of symmetry.
Tensor product over what?
Okay.
And how does C upper star of Y act on My?
Since when we choose capital My is a symmetry module, C star X as a C star Y module. We consider it as a C star Y module. And this action just by the epsilon. So because you have this map. Yeah. Okay. Okay. Okay, this is a quasi-isomorphism. Similar argument for H. For H, we use a notation here. Gamma. This is a gamma hat. If you remember what is M hat. And maybe I should record what is I should record again what is my hat. So you can consider this as gamma is my to.
Okay.
To
There's another thing which is not clear to me. My. Basically either this one or the other one is just a module.
Yeah.
We want to model C of F as an algebra. So what do we do? This semi-free resolution thing is works for modules. We resolve something as a module. Very well. But then what we get is again a module. with
Yeah.
C upper star of y.
C of star. This is a
Well,
I- I-
there's no algebra structure on the thing on the two things in the bottom row.
yeah you
There are modules. It's not exactly clear how to make them into algebras.
in this you just consider the action by k.
Yes, but we we want to multiply two elements of each of the things in the bottom row. I want to be able to multiply those. For example, my, how do we multiply two elements of my? And then there's a similar problem for the in the bottom left corner because C of y is not commutative. So if we have a tensor product of two commutative algebras and another commutative algebra, then the result is
Commutative.
the result is a commutative algebra. Now, if we have non-commutative algebras, then the only thing we can tensor multiply would be bimodules or modules. We can tensor multiply a left module by a right module if over a non-commutative ring. On the other hand, it's sort of hard to multiply algebras. Well, we can always multiply algebras, but what we get is still bimodules. Well, there's push forwards in the category of algebras in the non-commutative case as well as in the commutative case, but they're not given by tensor products.
Yeah, by right tensor product.